Welcome and thank you for joining us today for this SPE Tech Talk with TETRA Technologies. I'm your host for this broadcast, Joe Sinnott, and I'm excited to dive into the world of completion fluids, a world where cesium formates were the only viable option operators had to complete their wells safely, until now. That's because operators now have access to TETRA Neptune multi-use fluid, which provides a customized, cost-effective option operators can use to move away from expensive cesium formates, all while meeting all the environmental requirements for the Gulf of Mexico, the North Sea, and other sensitive environments. Plus, this fluid is formulated from renewable products, which means that it is consistently available. That being said, we're joined today by TETRA to wade into everything that makes this Clear-Brine fluid so unique. We'll discuss its evolution for use in diverse applications, and of course, we'll answer as many of your questions as possible. So please take advantage of this live broadcast, use that comment box to ask your questions and to share your thoughts about today's topic. Two other great ways to interact with today's show are one, to let us know where you are watching from, and two, to answer today's audience poll question, which is, where could TETRA CS Neptune fluid technology create value in your asset? A, as an ultra-low solids reservoir drill-in fluid in aqueous or non-aqueous systems. B, as a cost-effective alternative to cesium formate. C, as an environmentally compliant solution to replace zinc-based fluids. D, as a pad fluid for control line fluid compatibility. E, for use as an ultra-low solid screen running or packer fluid in aqueous or non-aqueous fluids. F, for use as an ultra-dense monovalent frac fluid. Or G, none of the above. Let us know your answers in the comment section, and we'll take a look at the results later in the show with our guest. And speaking of our guest, let's go ahead and introduce Richard Hay, who is joining us today from the Woodlands, Texas. Richard is Global Vice President of Completion Fluids at TETRA Technologies. Originally from Aberdeen, Scotland, he has over 34 years of experience in the oil and gas industry, as well as the renewable industry, serving in leadership roles in Africa, Asia, Europe, and the Middle East. Richard holds a Bachelor of Science in Chemistry from the Open University in the United Kingdom. With that, hello, Richard, and welcome to SPE Tech Talk.
Yes, good morning, Joe. How are you today?
Oh, I'm doing great. Again, I'm excited, and I know our audience is excited. And typically, our audience is pretty technically minded there, Richard. So if you would, let's just dive right in and, share some of the technology, share some of how, the aqueous chemistry expertise has led to an ability to engineer true and pressurized crystallization temperatures for demanding conditions that are faced by operators.
Okay, yeah, thanks, Joe. Thanks for that introduction. So in completing wells using solids laden fluids, such as oil-based mud, water-based mud, or even synthetic-based mud, the solids can impair reservoir production, damage the functioning of downhole completion tools. Therefore, completing wells with Clear-Brine fluids is the obvious preferred alternative. Completion brines are typically halide or formate salt solutions in water, but they too also have some shortcomings. At lower temperatures or increased pressures, the salts in these fluids can crystallize. This can cause potential well control concerns and or costly operational disruptions. Completion of high pressure wells with densities above 14.3 pounds per gallon for calcium bromide or 13.1 pounds per gallon for potassium formate has historically required the use of brines containing either zinc bromide or cesium formate to minimize formation damage. Yet, in addition to their merits with both fluids, both of them have inherent liabilities. An example of zinc-based fluids, they're restricted, classified as priority marine pollutants in many locations due to their potential harmful effects on the environment. They also have a low pH or low acidity, with zinc-based halides increasing the potential for corrosion of metal components and of course, risk to personal safety. There are also concerns around handling zinc-based fluids at gathering stations. This is becoming increasingly prevalent, especially in the Gulf of Mexico, and with respect to receiving zinc halides. With formate fluids, which I must note is an excellent technical option in many cases, the limited production may restrict supply and lead to higher costs in high volume deep water applications. Now, moreover, when used as a backup fluid, literature has suggested, and I referenced Javora 2003 here, suggests that formates may cause hydrogen-induced cracking in high-temperature wells and in the presence of corrosive gases, which could lead to failure of production tubing. And looking at other motivations that they create the need or desire for a new high-density brine could include, there's an increasing number of deep wells in deep water, new plays coming into effect, the creation of an alternative that can achieve other functions, multifunctional, even cost efficiencies. And of course, there is, in some cases, a lack of availability of certain formate material due to limited supply and inventory. So how did we get to the point where a new chemistry was required? Well, as the saying goes, necessity is the mother of all invention. And the genesis for the development of the novel aqueous chemistry was when a major US operator asked TETRA to help develop a novel Clear-Brine fluid for a major deep water Gulf of Mexico project. It required properties of 15.4 ppg with a pressure crystallization temperature of less than 30 degrees Fahrenheit at 15,000 psi. Now, as mentioned, the only alternatives were, from a true crystallization temperature standpoint, i.e. solutions that would be thermodynamically stable at these temperatures and pressures, were zinc brines or cesium formate brines. However, both of these gave rise to several concerns for the operator. Again, zinc wasn't acceptable for this operator due to high corrosion rates, but moreover, the environmental reasons and the toxicity to marine life ruled it out. And with the traditional high-density fluids, the alternatives, there was a major cost issue, and the inventory available worldwide to service the volumes of this deepwater project was restricted and wouldn't meet the expectations. So the challenge for us was to design a novel fluid that was stable at the temperatures and pressures and address the concerns of brine crystallization associated with heavy brines. So can you bring up the first slide, please, if you can, the graph. So the central design philosophy was on engineering true crystallization temperatures, or TCTs, which required the development of novel crystallization suppression technology. TCTs are the crystallization temperature of oil fluid brines, which is a function of dissolved salt concentration. Now, this relationship is not linear, and there is an inflection point, otherwise known as the eutectic point, which represents the lowest crystallization temperature achievable with a specific brine chemistry. So referencing the graph on this slide, plots of crystallization temperature versus brine density, i.e. salt concentration, typically follow for a calcium chloride and calcium bromide brine system as illustrated in this graph. Each brine system has its own phase diagram. And our objective was to shift this eutectic point to the right using novel aqueous chemistry. So as long as the brine density is less than the density at the eutectic point, increases in brine density lower the crystallization temperature. Now, in contrast, densities above the density of the eutectic point raise the crystallization temperature. For example, the eutectic point for calcium bromide brines occurs at approximately 13.2 pounds per gallon at minus 57 degrees Fahrenheit. Correspondingly, at 14.1 pounds per gallon, calcium bromide exhibits a crystallization temperature of approximately 10 degrees F. So you see the inflection there. However, with increasing density at 14.9 pounds per gallon, the crystallization temperature of calcium bromide brines rises to approximately 57 degrees Fahrenheit. And obviously the fluid is no longer considered viable for many well applications. So each brine system has its own phasogram, and our objective with designing the novel chemistry was to shift this eutectic point to the right.
Got it. So Richard, hearing you talk about, obviously, there's going to be a range of densities. You talked about some of the motivation for, one particular client, particular situations. How do you assess, or how do you describe the value for customers who might be looking at, a range of densities, or perhaps, looking at both, monovalent and divalent formulations? Can you talk a little bit about just the thinking behind that? If you're a customer and you're going to be looking at all these different scenarios.
Yeah, so the development of a novel crystallization suppressants enabled us to develop a range of Clear-Brine fluids that are able to cover the density range than the required operational TCTs, with the brines that do not contain zinc or other priority pollutants or rely on formates. If you could bring up the next slide, please. So referring to the slide, you can see that we've developed a robust offering of monovalent and divalent fluid lines, capable of maintaining desired properties and performance through expected life of completion of production. Again, the main feature of this is the lower crystallization temperatures, pushing your TETRA point to the right. And, when it comes to which one do you choose, obviously there's a density requirement, there may be a reservoir chemistry, maybe cost and corrosion. In some cases, monovalents can offer better reservoir compatibility depending on the interstitial chemistry of the formation. Other times, the best option for cost may be a divalent option. So we have a range, you can see from the graph. In the monovalent applications, your densities can be extended from 12.3 to 13.1 ppg for the high density monovalent technology, through to 15.4 for the extra high density application. Both of these systems can be stable up to 350 degrees Fahrenheit. For the divalent applications, densities from 11.6 to 15.4 through to 17.5 ppg are possible, with temperature stability again up to around 350 degrees Fahrenheit. Now, as you would expect, there would be, or there is, a very wide range of costs across the density ranges. However, depending on the well parameters, significant savings can be made versus mechanical or alternative high-density brines, especially at the lower density ranges where the Neptune multi-use fluid system can be very, very economical and significantly lower well construction costs. As a footnote, within each valency, monovalency or divalency, the chemistries are interchangeable and fully compatible. So efficiencies can also be achieved with hybrids of system. It's really all about, as with many things, custom engineering the cost advantage. And there are a number of alternative chemistries in the Neptune multi-use fluid system that can be fine-tuned to provide these cost-effective solutions.
Got it. All right. Well, thanks for the insights there. And again, thanks to our audience. I encourage you all, continue asking your questions, sharing your comments. Clearly, we have an expert here. We want to get to as much of your feedback and your input as possible. But for now, again, as always, I got plenty of my own questions, Richard. So kind of building on what you just said, right? There's a range of opportunities. There's a range of scenarios. So how do you keep expanding the possibilities, to use, this technology, right? Especially when we're talking high density, formate free, zinc free fluids. How do you go from, I guess where you're at now or where you were at and evolving this into multi-use applications?
Okay. Yeah. Thanks for that question. This system started off as a completion Clear-Brine fluid. And aside from that application, which was the original design premise for the novel crystallization technology, these applications are multifaceted. And over the past 18 months, it's really evolved to a multi-use, multifunctional, high-density fluid system with zinc-free, zero solids or ultra-low solids applications. Some of these applications may include reservoir drilling fluids use, RDF, or drilling fluids, as otherwise known. And it can be used as a base brine for a water-based drilling fluid, or as the discontinuous brine phase in an invert-based drilling fluid. With the high-density Neptune brine offering a significant reduction in solids loading, enabling ultra-low solids concentrations, allowing the minimum solids required for bridging the pore throats to form a thin, non-damaging filter cake, and possibly allow for higher ROPs due to reduced solids. When you look at formulating traditionally drilling fluids or reservoir drilling fluids with sodium bromate, potassium formate, the limitation of these brine types is clearly density. Sodium bromide is limited to approximately 12.3 ppg, and potassium formate to 13.1 ppg. When the reservoir drilling fluid is formulated with, say, an optimum 50 pounds per barrel of ground marble as a weight and bridging agent, an overall density of 13 ppg can be achieved with sodium bromide, and a slightly higher density with a potassium formate at 13.7 ppg. However, when solids, higher densities are required, more solids must be added to the fluid, increasing the risk of formation damage. The higher density of the TETRA Neptune extra high density monovalent fluid, 15.7 ppg, means that a reservoir drilling fluid containing only 50 pounds per barrel ground marble can achieve a density of over 15.8. So we're continuing to research the expanded envelope of where this technology could be used. We've done extensive formulating and engineering over the past 18 months on reservoir drilling fluid opportunities, using a 14.75 pound per gallon monovalent system and very limited calcium carbonate as a weighting or bridging agent. We can get a final density of 15.1 pound per gallon. We've seen excellent rheology, low-end rheology, high-end rheology gels with xanthan and starches, and static aging at 72 hours at 250 indicated there was no degradation in any rheological properties. On the sort of divalent side, we've been successful in formulating reservoir drilling fluids at densities of 15 to 16.5 pounds per gallon. Unlike the monovalent and divalent systems are more tricky to obtain the optimum rheological profiles with acceptable filtration properties. However, we found that with specialty and modified starches, the systems are provided exceptionally well up to 280 degrees Fahrenheit. Again, with the monovalents, we've observed excellent YPs, PVs, low end and gels. 7 days static agent, 280 degrees Fahrenheit. They not degrade the properties significantly. And we're also currently engineering a 16.5 pound per gallon reservoir drilling fluid for use in a major deepwater project. In this instance, with the higher brine densities offered by the Neptune multi-use system, we're able to reduce the solids load in the RDF by 40%. That can be achieved with traditional calcium bromide. Extensive flow testing as well of return permeability, so otherwise known as being undertaken in both Neptune-based brines and our formulated reservoir drilling fluids. In these instances, substantial improvements are seen over and above the performance of calcium bromide or zinc bromide solution, with a 50% improvement in return permeability. There's also the advantage that a system reservoir drilling fluid based on a Neptune fluid could be converted to a Clear-Brine completion fluid or screen running or placker fluid. Given the very low solids content, this could be screened out, polymers broken down if required, and the fluid reused in the completion interval. Needless to say, this would offer considerable cost savings as well as logistical and well-timed benefits. Where the novel high-density brines are not used in the reservoir drilling section, of course, the technology can be used as standalone packer fluids or screen-running fluids. Another application is in solids-free or ultra-low solids invert emulsions, where a non-aqueous fluid is required and the presence of solid weighting agents is undesirable. For example, when running sand screens into the hole. To achieve significant density in these fluids, it's necessary to formulate them at very low oil-water ratios, typically 40-60 or below. And achieving the acceptable fluid stability in such a low oil-water ratio is notoriously difficult. Formulating a 40-60 ratio fluid with a commercial 14.2 calcium bromide provides a density of 11.2. However, if we replace the calcium bromide with a TETRA Neptune 17.5 pound per gallon, then a solids invert, free invert mud can be obtained with a much higher density of around 12.9 ppg. Another application, the system can be used in slugs to avoid water treatment as a practical cost-saving application that avoids brine spillage on the rig floor, saves brine costs obviously, and avoids excess brine on the drill floor, which with obvious HSE benefits. And another very, very recent development has been the engineering of a pad fluid compatible with control line fluid for BOP stacks. One operator had issues with control line fluids forming hazardous emulsions with zinc bromide completion fluids. This resulted in an inability to flush these from the BOP stack. An engineered solution would have required a 12 million retrofit to the stack. TETRA was asked to provide a solution, and we designed an extra high density divalent Neptune pad fluid at 16.5 ppg. This system is formulated, engineered, and risk assessed, and that will be deployed later this year on a US operator's major capital asset in the Gulf of Mexico. And finally, the system may have applications in large volume fracking operations, especially at the lower densities where sodium bromide is utilized. Some preliminary testing with service company partners has shown that a standard 12.5 ppg sodium bromide can be economically extended to 13.1 pound per gallon or slightly higher, in effect allowing for a denser fluid column or effect a larger hammer to frac the formulation. So just in summary, we see the technology being more widely used in the reservoir, either as an aqueous or non-aqueous reservoir drilling fluid, leveraging the zero ultra low solids possibilities. And I think from an industry, as we go into deeper and more deep water assets, this will continue to be a requirement.
Great. Well, thanks for stepping through those details. I know, again, we got at least one question from Surrenda on Energy Stream, and I think you answered a lot of what she asked. She was asking for, hey, what are some of the studies showing? What are some of the rheological data? So again, Richard, you just answered some of that there. We'll keep moving on here. But again, thanks to Surrenda and everybody else who's asking questions there on Energy Stream and all of you who are watching. But again, moving on from some of the technical stuff, Richard, again, you're talking about, hey, this stuff works. Here's how it works. But in this day and age in our industry, it's tough to escape the big question, which is sustainability. You just gave some examples of customers looking for solutions, but increasingly, right, they're looking for sustainable solutions. So can you offer just a little bit of insight on how, your product aligns with that hunt for sustainable solutions in this current world that we live in?
Yeah, so please do. So, as we're all aware now, an important part of developing any new technology is really understanding the total life cycle of a product, and it's particularly the impact on carbon emissions from cradle to grave. Central to ESG policies, and it is clear that minimize environmental impact is important. I mean, it's a right thing to do from a societal perspective, but mostly what I found it's a best business practice and creates efficiencies. So the Neptune technology is based on readily available chemical components that can be sourced from a variety of global locations. This means that the technology can be supplied from the regions where the project is located. It's really important. So this contrasts with some other traditional alternative brines, especially those based on rare minerals, which may also be mined in a limited number of deposits worldwide. This means traditionally that there's long supply chain routes, which result in greater overall emissions, clearly, with the shipping across the globe. And another important note is that the chemistry in the Neptune systems is from sustainable, infinite sources. So additional features or advantages not yet covered are the environmental compliance. This was obviously a key aspect, when we're designing the system to improve upon what's available at the moment with zinc, for particular, which is a marine polluted and highly toxic. The technology had to meet or exceed regulatory compliance in the strictest of environments. The Neptune technology meets environmental approval for both in the North Sea, both the UK and Norwegian sector, arguably the strictest regulations globally, and of course in the Gulf of Mexico. So just to recap briefly, in the US, it meets all the EPA, MBTES, Clean Water Acts regarding oil and grease sheens and priority pollutant requirements. In the UK, all TETRA Neptune fluid components are E or gold rated. There's no substitute warnings. And in Norway, all TETRA Neptune fluid components are yellow rated. So just finally, another key design feature of the Neptune is reuse and recyclability. Very important. It's not a one-shot solution. So with judicious treatment, of course, discipline and best practice at the rig site, and importantly, engineered displacement techniques, we'd expect that operators will recover the majority of fluid, significantly, of course, reducing the environmental impact and cost impact. And typically, upwards of 90% recovery would be a anticipated KPI for any project.
All right. So I think so far we've covered a lot of the technical aspects, right? We've talked about the sustainability aspects, Richard. And now the question on most people's mind would be economics. And I say that not just as a general statement, but because we asked a question of our audience earlier about, hey, where do you see the most value potential for this product? And our answers overwhelmingly were for B. I'm not going to read through all the options from earlier, but it looks like most people said, hey, I see this as a potential cost-effective alternative to cesium formate, which I guess leads me to the follow-up question there, Richard. Can you talk about the economics of this? Can you talk about how the products we're talking about here, the CS Neptune fluid, compares to formates?
Okay, yeah, thanks a little bit. So, as we mentioned a couple of times, high density fluid solutions are expensive, regardless whether a traditional or novel. Once you get up to the very high densities, it can be very expensive. And especially traditionally the blends containing rare minerals. Due to the rarity of these minerals, from a finite resource and mined from very limited commercial deposits in a couple of locations, the novel suppression agents developed from the Neptune system facilitate a very cost-competitive alternative. The key again is really in customization and in engineering the solutions to meet the customer's value drivers and technical needs. As you may expect, with a density of range from 12.5 pound per gallon to 17.5 pound per gallon, systems will have a wide range of impacts, from surprisingly low-cost options at the larger densities to the more expensive at the higher end of the density spectrum. Of course, and I must note here, zinc or formates or other mechanical options may be the right application in some instances, but the industry now has another option in the toolkit to consider.
Got it. So kind of building from there then, whether it's economic challenges and making projects work or some of the other, technical challenges, what do you see as current challenges that asset owners face right now that, again, call for something like what we've been talking about here over the last 25 minutes?
Yeah, thanks. Well, I think, with the increase in deepwater assets, with deeper wells, there comes a requirement for higher densities. So we need to continue to push the technology, and we are working on other novel aqueous chemistries to see how we can extend that density range. But, with deeper wells comes higher temperatures and a requirement for higher temperature stability. And I think, increasingly, we cannot use zinc due to the metallurgy of the gathering stations or processing facilities. And even small amounts of zinc can lead to costly production shutdowns. And zinc used in completions can offload later, when the well is brought into production. And this can create previously unplanned time or cost. In summary, I think with these deeper and hotter wells, corrosion control will become more challenging and may require the industry to look at novel inhibition chemistries to minimize risk of corrosion.
Got it. All right. Well, let's see here. We got a couple other questions coming in here. Maybe a little bit of rapid fire, Richard. One, let's see. When it comes to reclamation or restoration, so how do you get back to initial properties if the Neptune is heavily contaminated with unknown contaminant, which can change the properties, perhaps radically change those properties? How do you deal with that, Richard?
Well, it's like any other clear brine fluid. It's mitigation, prevention of the contamination is important. So displacement techniques, engineered displacement trains are critical, as with flow regimes, etc. Well, when it comes to treatment, on the well side, apart from dilution, we can use filtration aids. Traditional diatomaceous earth or cartridge filtration doesn't strip the suppressant. The suppressant is totally immiscible, so it's part of the fabric, the fluid. There's no way to remove it apart from dilution. Filtration aids that remove hydrocarbons, oil, and grease do not strip the crystallization suppressant either. And it's a fairly easy system to manage. So we do have some patented processes around reclamation when when it's finished with at the well site, for example, and it gets taken back to the brine plant. We have other further techniques and tips to reclaim. And again, upwards of 90% reclamation is the anticipated metric.
Got it. All right. Let's see here. We're closing in on the end of our show here, but we got plenty more questions. We got one from Rakesh. So he asks on LinkedIn, why only brine fluid? Why are we talking about just brine from a compilation process standpoint? Can you talk about why, or the importance of kind of focusing on that?
Okay, maybe repeat that question, please. I didn't get all of it.
Well, he's got it listed here as why only brine fluid is used as a compilation process. I don't know if you're talking from a comparison standpoint, or how does our focus on brine right now for this Clear-Brine CS Neptune idea. What's why aren't we looking elsewhere? Is there something other than that, Richard? That we
I mean, TETRA, we are a brine company. That's our core competency. Okay. We manufacture our own brine. We're a vertical supplier in the industry through the providing service at the rig site, and we're all about aqueous chemistry. And as I mentioned in the preamble, solids in fluids, whether it be water-based fluids or non-aqueous like oil-based fluids, create problems for tools. So our focus was on delivering on an industry need to provide technology that's more environment compliant, i.e. against zinc. It's a very toxic marine pollutant. So find an alternative for that. and for the higher density traditional alternatives, which are very, very costly. So that's the focus on brine fluid. If that answers this question.
Yeah, well, it answers my question, at least. So I appreciate those
Okay.
insights. I guess to kind of wrap up here, what else do we need to know? What other details, what other field applications are we talking about with this new technology, Richard? What else does our audience need to know here so that they can move forward and again, take full advantage of this new innovative technology that we've been talking about here today?
I think what I'd like to emphasize here is that the opportunities for use as a reservoir drilling fluid, or a drill-in fluid, or any other ultra-low solids applications in the wellbore is multifaceted. There's many opportunities here to reduce solids loading very considerably. I mean, when you reduce solids loading, you get better filter cakes, better formation protection, arguably higher rate of penetration, so it can be very slow in the reservoir section, as well as reducing the cost. And the other aspect that I'm looking forward to exploring is the multifunctional use of, say, for example, Neptune as a reservoir drilling fluid that's then converted into a completion brine fluid or a screen running fluid or a packer fluid. So you can get one system or three systems for the cost of one or 1.5 systems. So that's what I'm excited about.
Great. All right. Well, thank you for sharing that. Thank you to everybody who asked questions. Again, if we didn't get to your questions, keep them coming. If you're watching this on demand, keep adding those questions in. And again, we'll try to get to as many of those asynchronously, if you will, after this show. For those who want to reach out to you directly, Richard, with any questions or seek more information, what's the best way for them to get a hold of you?
Yeah, just reach out direct. I think my email is available via this event. So please reach out direct and I'll answer any questions you have to the best of my ability.
All right. Well, there you go, audience. You heard it. You heard the invitation. Richard's available for all your questions. Again, Richard, thank you for all the insights that you shared today. Thank you for answering all of the questions that we were able to get to today. Want to give a special thank you, of course, to TETRA Technologies for making today's conversation possible. And if you or somebody else would like to watch a replay of this conversation, you can do so by heading over to the SPE Energy Stream, the industry's digital pulse. Visit streaming.spe.org. I'm your host, Joe Sinnott. Join us again next time right here on SPE Tech Talk.
In a rapidly evolving energy industry, you need to stay ahead of the curve with relevant content available when and where it's convenient for you. You need the upgraded SPE Energy Stream, the global platform for high-quality content with the energy industry. Fuel your energy career with Energy Stream's sleek new look and easy access to top-quality technical solutions, insights and innovations, trending topics, thought leadership, market outlooks, and education. From original programs to exclusive SPE event highlights, this exciting, easy-to-navigate platform features insightful content delivered live and on demand. Explore insights from industry thought leaders. Then save the videos that interest you and watch them at your convenience. Be at the forefront of energy knowledge and explore the newly updated SPE Energy Stream now.